Okay, so welcome to everybody to this colloquium of the Physics and Astronomy Department of Padova. So today we have actually the pleasure to host Vincent Vennin, who is a CNRS researcher at the Ecole Normale Supérieure in Paris. Before leaving the word to him for the colloquium, just a brief introduction. As usual, Vincent Vennin actually got his PhD at the Institute of Astrophysics in Paris. Then he moved to UK in Portsmouth, actually as a postdoc at the Institute of Cosmology and Gravitation. And then actually he came back to France and he got a permanent position as a CNRS researcher, working actually in the first stage of his career at the Astroparticle and Cosmology laboratory in Paris, and then recently, actually 3 years ago, he moved to the Ecole Normale Supérieure at the Physics department, where actually he started, together with Cédric Defayet, a new research group focused mainly on theoretical cosmology and different aspects of gravity in cosmology. Now, one of his main research interests, which will be actually also the focus of the colloquium, is about the physics of the early universe, inflation, how actually from quantum fluctuations then you generate the seeds which bring to the large-scale structure of the universe. And recently, actually, and this is also one of the reasons why we invited him, he did very interesting works on actually how to apply foundations of quantum mechanics and also of quantum sciences to cosmology. So it is a pleasure to have Vincent here, and I leave the word to him. Just before starting, just let me remind you also the next colloquium, it will be on the 6th of June, Thomas Stoker, about actually climate change. Okay, thank you, Vennin, you can start.
Well, thank you. Thank you very much, Nicola, and let me thank you for the very kind invitation to come to Padova. I'm sorry that it seemed I brought you the bad rain and the bad weather from Paris. I promise that when I leave tomorrow, I take the rain back with me and you can go back to your nice weather, nice Italian weather. So the title of the talk is Can we prove that cosmic structures of quantum mechanical origins? And I will divide the presentation in two parts mainly. The first part will be devoted to explaining why we think that cosmic structures, so galaxies, stars, and so on, come from quantum fluctuations, why this is the leading paradigm to understand the physics of the universe today. So this will be an introduction to the field of early universe cosmology in which I'm working. And then the second part, I will try to explain how we can test this hypothesis and is there really something quantum in cosmological structure that we could try and show. So cosmology has many fields of science, is driven by observations. The difference between cosmology and other fields probably is that in cosmology we can't really make experiments, right? The universe is given to us once for all and we cannot just make universes in the lab and make experiments on them. But however, we can make observations of the universe in which we live. And one of the starting points of modern cosmology is this measurement made by Hubble in 1929, who observed the distance and the velocity of typical objects in astrophysics, which are called Cepheid stars, which are a typical type of stars for which we can for which we can measure the distance and the velocity at which they move away from us. And so this is the figure which is taken from this 1929 paper. Of course, nowadays we have versions of this figure which are much more convincing. But if you, with a little bit of faith, you can imagine indeed that there is this correlation which is displayed by this line. So the velocity at which those stars move away from us increases as the distance between the Earth and those stars increases. And Hubble conjectured that there is a linear relationship between those two quantities, so the velocity is proportional to the distance, and the parameter in this equation is called h because of Hubble. So this is called the Hubble parameter. This equation is called the Hubble law, And if you trust the values of this graph, you find that the Hubble parameter should be around 500 km per second and per megaparsec. Megaparsec is a unit of distance in astrophysics. And this measurement is not so bad because the true value is around 70 instead of 500. So it's only a factor of 10, but in the early 20th century, a factor of 10 was a very high precision in cosmology. So why this law is important is because it tells you that that space is expanding, right? That stuff are moving in space, and of course, if space is expanding, then the velocity at which objects are moving apart from the other increases with the distance. So this was the first evidence that the universe has some dynamics. And so the way to interpret this fact, this observation, is to use a theory of gravity, which is general relativity. And in general relativity, there is a link between the way that space-time is curved, and actually when space is expanding, it means that space-time has a curvature, and the thing which is inside space-time, okay? So the matter which you have put inside the space-time. So those two objects, they are described by those two tensors in Einstein equations, so G mu nu and T mu nu. And this equation tells you that if you can measure or if you can constrain the curvature of space-time, so typically the rate at which space expands, then you can gather some information about the stuff that is inside the universe, which makes space expand. So when you apply this equation, what you find using multiple astrophysical measurements at multiple times in the universe is that the universe has this composition. So the majority of the universe is made of what we call dark energy, which is called dark, mainly because we don't really know what it is. Right? So it's a form of energy which has one particular feature, which is that it does not seem to dilute. So the energy density of this guy remains constant, or is consistent with something that remains constant, even though space expands. You would expect that if you increase the volume, if the energy is conserved, then the density should go as 1 over the volume, for instance. But in fact, there is a component of the universe which does not dilute, and so there are several possible explanations for what that guy could be, but we don't know yet. Then the second, what comes second is called dark matter, so it's dark again, and again it's dark, which means we don't really know what it is. So this dark matter is matter, so this time it's something which indeed dilutes as 1 over the volume. When you increase the volume, the energy density goes as 1 over the volume. However, it's a matter which do not emit light, or at least we do not see it when we observe the universe through photons. Okay, so there seems to be some form of matter which poorly interacts with photons, but which nonetheless leaves some gravitational imprint. And then the rest of the stuff is things which we actually know what it is. So usual matter, the particles of the standard model of particle physics, and a small amount of light and of neutrinos. So what to take away from this figure is that basically the majority of what constitutes the universe is something which we don't yet know what it is. But of course, by measuring the universe in different ways, we can hope to learn more about those things. One interesting aspect of cosmology is that it's a so we usually combine different ways of constraining what the universe is made of. And one way is, as I said, is to measure the rate at which the universe expands. But another way is to look at the way that structures form in the universe. So here you have some numerical simulation from a collaboration which is called the Illustris collaboration, in which you can see a universe which starts with an initial condition which is almost homogeneous. But then because of gravitational attraction, when there is a small overdensity somewhere, it attracts more matter. And then you have structures which start to form at different scales. So in galaxies, but galaxies are organized into those kind of filaments, and between those filaments you have walls and you have voids and so on. And one of the main lessons of those numerical simulations is that the typical statistical distribution that you obtain at the end, so say at the end of the simulation you see where you have formed galaxies and where those galaxies are distributed in space. And the main features of those statistical distributions is related to the ingredients of the simulation, that is to how much dark matter, how much dark energy you have put in your simulation, what are the properties of the dark matter field, and so on. So by comparing the output of those simulations, I just show you another one which is slightly bigger scale. By comparing the output of those simulations with actual observations that we make of the large-scale structure of the universe, we can constrain, this is another way to constrain the constituents of the universe and how they act on the formation of those structures. So those are only two examples, but there are many different independent measurements you can make in astrophysics and cosmology, and which all sort of combine and give rise to a consistent picture, which we call the standard model of cosmology. So there is a standard model in particle physics. There is also one in cosmology nowadays. And the standard model of cosmology is called the Big Bang model. And it tells you the following story. So this is just a nice sketch. Here times goes from the left to the right. So observations are consistent with the following thing, that the universe expands as a function of time. So it starts out in a state which is very dense, very hot. And as time proceeds, it gets bigger, so it gets cooler and less dense. Initially, we observe that the universe is almost homogeneous, so there is almost the same amount of matter and energy at every point in space. But as time proceeds, because of gravitational instability, as I was saying, you start to form structures and galaxies and so on. We are somewhere here. There is a red dot here, which is supposed to stand for the solar system in the Milky Way. But it goes through a certain number of events as the typical energies decay as a function of time. So what is interesting with this picture for theoretical physicists is that if you go back in time, the energies at scale become larger and larger, which means that if you are able to perform observations of the universe at an early stage, it means that you're constraining physics at a high energy scale. And you know that there are not so many ways to understand physics at different energy scales. The most straightforward way is to build particle accelerators. You build particle accelerators, and then you accelerate particles to a very high speed. You create a collision, and then you can describe physics at the scales at which the collision took place. But there is, of course, a limit to that. We cannot go to arbitrarily large energies. The LHC goes up to, say, 1 TeV or a few TeV. And we can maybe hope that if we build a bigger accelerator, we can go to even higher energy scales. But, at some point, there is a limit to that process. The nice aspect with cosmology is that we can go to much, much larger energy scales. And in fact, the phase that I will focus on today, which happens at very, very early time, which is called inflation, I will explain what it is in a minute, is expected to take place at energies which could be as high as 10 to the 14 GeV. Okay, so many, many, many orders of magnitude above what can be done in accelerators. Of course, it's not as easy as in accelerators because, again, it's not an experiment, it's just an indirect observation. But still, it bridges the gap between what we can probe on Earth and scales which are not so far from, say, the highest scale of quantum gravity or something like that. In this picture, you can see on the left this image, which corresponds to what is called the cosmic microwave background. So one of the main predictions of this Big Bang model is that there should be a time, so very early on in the universe is expected to be opaque, which means that even though photons exist, they very often scatter off charged particles like protons and electrons. So light does not travel in a free way. Okay, photons, they do not travel as a straight line. And so this phase of the universe, which is very dense, very hot, we cannot observe it with light just because light does not escape from it. Okay. It's as if you wanted to observe the center of the sun with light. You cannot do it directly because light does not go from a straight line from the center of the sun towards you. You only observe the outer part of the sun, which is less dense. And then at some point, because the universe expands, what happens is that electrons combine with protons, they form hydrogen atoms. This is called recombination. And then the density of those atoms decreases as well, and photons start to propagate in a free way, as a straight line. So this background of light continues to travel throughout the universe. And even today, the room is being crossed by such photons. Okay, of course, we don't observe them. You don't observe them with your eyes because they are super low energy, but nonetheless, they exist. So there is this prediction from the Big Bang model that there should exist a background of photons with a very low temperature, which is called the cosmic microwave background, and which was indeed observed in 1965 by two physicists, Francis and Wilson. And this discovery is also one of the landmarks of cosmology because it confirmed the validity, or say it did not confirm, but it reinforced this Big Bang model which predicted the existence of this background of photons. An important observation is that, so there are two main things to notice. One is that the photons that we receive, they are in thermal equilibrium, okay, so their energies is distributed with a Boltzmann law, with a temperature which, as I was saying, is very low, is 2.7 K, okay, so only 2 degrees above the zeroth temperature. And also that temperature seems to be independent of the direction along which you perform your experiment, okay, so if you point your telescope towards this direction, you receive photons and you look at, you measure the temperature of those photons, you find 2.7 K, but then if you change direction, you will find again the same temperature. So we say that the universe is isotropic, which means whichever direction you choose to observe it, you find the same answer. But in fact, people after 1965 tried to see whether we could find some fluctuations away from this 2.7 K value. And this was done by mainly a series of experiments, but 3 main satellites at least. The first one was COBE in 1992. So here what you see in this map, the color stands for the temperature. There is no scale, but I will show you a scale in a minute. But it is a very, very tiny fluctuation of the temperature. So they took the temperature and then they subtracted this mean value, this 2.7 K. Okay, so it's only the fluctuating part that you see. The red regions correspond to slightly hotter photons and the blue regions to slightly colder photons. The red stuff in the middle has nothing to do with cosmology. It's the galactic plane. Okay, so the orientation of this is such that the equator here corresponds to the plane of the galaxy. And of course, when you try to observe the CMB by aligning your telescope with the plane of the galaxy, you get a lot of contamination from the stuff which is close to you in the galaxy, so dust and other sources of light in the galaxy. So this has nothing to do with the cosmic microwave background, it's just a contamination effect. And this was measured again in 2003 by WMAP, where you see that the angular resolution of the measurement improved. Also, the contamination from the galaxy is also a little bit smaller. And this is the most recent measurement we have from the Planck satellite. So in fact, the image that you see on the screen is, I think, maybe a little bit compressed by the projecting device, but the angular resolution is really tremendously better. You see the scale of those fluctuations is of the order of the 100 of micro Ks. So it's a very, very tiny fluctuation of the temperature. The delta T over T is of the order 10 to the minus 5. Okay, so it's 1 part in 100,000. So it's a very small fluctuation. This is why it's very challenging to measure. You see also that there is no contamination by the galaxy because Planck was able to remove the contribution from the galaxy by doing some things that I don't have time to explain. But this image is to basically convey the fact that this cosmic microwave background has been measured to a very high degree of accuracy, not only the mean temperature, but also all the fluctuations in the temperature that we have. So I will explain why those fluctuations of the temperature field are so important for us. But basically, the reason why they are very important is that this is the oldest picture of the universe we can have because it's the very first light. Okay, remember that before this time, the universe is not transparent, so we cannot observe it. And therefore, this is the furthest we can go in time. So it's the best way that we have to constrain physics that occurred before this moment of emission of the cosmic microwave background. Okay, this is just a comparison of the 3 measurements to show you in 20, 30 years how things improved. Okay, So this Big Bang model is very successful. It explains many, many things that we observe. There is the cosmic microwave background. There are other things which I don't have time to detail, but there are lots of measurements which are consistent with the model. However, in the early 80s, people started to get a bit concerned with what was called the hot Big Bang model problems. So they are not really problems in the sense of they don't disprove the model, but say they are strange coincidences that are difficult to explain. So the most famous one is called the horizon problem. I will quickly explain what it is. So the idea is that, okay, in general relativity, the geometry of space-time is described by a metric, by a line element, which associates some distance to two events which are separated in time by some dt and in space by some dx. So if you live in flat space-time, which you do effectively most of the time, the metric is very simple. It's ds squared equals minus c squared dt squared plus dx squared, where c is the speed of light. But if you live in an expanding background, which is a curved space-time, you get almost the same metric. The only difference is that the spatial part is now being factored by some free function of time, a of t. Okay, so this a of t function is called the scale factor. And if you wish, if the universe expands, the a of t function increases. A of t is like a measure of the size, quote unquote, of the universe at some time t. If you live in a contracting universe, the a of t function decreases. Okay, so this metric is called the Friedmann-Lemaitre-Robertson-Walker metric. And with it, you can study the motion of different bodies. And in particular, you can study the motion of light. So the way that light travels in those curved metrics is by following what we call null geodesics. So null geodesics, they are paths which are such that the distance along the path is always 0. So ds squared equals 0. And if you equate this to 0, what you find is that dx becomes c dt over a. Okay, so if you follow the distance traveled by a photon, what you have to do is to integrate this 1 over a function. So it's the c times integral of dt over a. And if you want to convert it to a physical distance, you have to multiply it again by the value of the scale factor at the time at which you receive the photon, say. So this is why there is this a of t naught expression here. So this equation tells you the distance traveled by a photon between the time that it is emitted and the time at which you observe it. So now let's imagine that the universe expands. So you start from an initial point which we call the Big Bang. So this is the point where the a of t function goes to 0. Okay, so of course this point is a bit weird, but mathematically we can consider it. And let's consider the distance that a photon would have traveled from the Big Bang until today. Of course, it's an academic question because at the time of the Big Bang, we don't even know if photons exist and so on, but still, formally, we can consider this distance. So what you would have to do is to perform this integral for the a of t function, which describes the universe. Now you see immediately something, which is that if your time of emission goes to 0, if the scale factor goes to 0 in the past, you have to integrate a function which diverges. And then you can either get a finite result or an infinite result. It depends on the way that this function diverges. So let's take a very simple parameterization. Let's assume that the scale factor grows like some power law of time, which in practice is in fact a good parameterization for most phases of cosmology. So what you know is that, okay, if a goes like t to the power p, whether or not this integral converges depends on whether p is smaller than 1 or bigger than 1. So if p is less than 1, the 1 over t to the p function diverges, but the integral converges, which means that if p is less than 1, you have a finite result for this d naught parameter, but if p is greater than 1, d naught becomes infinite. And now, so what is the value? So the threshold question is what is the value of p? But in fact, in the standard model of the standard Big Bang model, p is always less than 1, which is not too difficult to understand why. It's because, gravity is an attractive force. So even if a dot is positive, at some point you expect the expansion of the universe to decelerate because, the different things in the universe should attract themselves. And so it means that a double dot should be negative. And if you differentiate t to the p 2 times, you get p times p minus 1. Times t to the power p minus 2, and for that to be negative, you need p to be less than 1. Okay, so if gravity is an attractive force, and according to in the standard model, P is less than 1, and therefore this quantity is finite. So this quantity is very important. It's called the cosmological horizon. And it tells you, if you take yourself and you draw a sphere around you, the radius of which is given by this d naught, it tells you all the points in the universe which could have influenced you today. Okay, the reason is that if those points, they sent a photon towards you at the time of the beginning of the universe, this photon has reached where you are before today, and so it can have some influence on you. And because nothing can travel faster than the speed of light, if a point lies outside of this sphere, it cannot have any influence on you, because even if it shot a photon at the beginning of time, this photon would not even have reached you yet. So there is no causality between this very far away point and yourself. So this is why d naught is called the horizon, the cosmological horizon. And here we see that in the standard model, d naught needs to be finite. So there is a finite size of your causal patch. You live in the region of the universe. You can draw a finite sphere around you. And anything which is outside this sphere cannot have any influence on you. So of course, we can compute this d naught more precisely, okay, if we assume that the universe is made of dark energy, dark matter, regular matter, radiation, and so on, with the proportion that I showed you before. You can do the calculation. And what you find is that at the time of the cosmic microwave background, the size of this cosmological horizon is rather small. Okay, so if you look at the sky and you take a causal patch at the time of the CMB, it's a little bit like, it's the same angular diameter as the moon. Okay, so it's of the order 1 degree. And if you try to take the moon and copy-paste it across the entire sky, you can do this around 450,000 times. Okay, so if you believe in this, the prediction should be that the cosmic microwave background is made of 440,000 patches, which are completely independent one from the other. And therefore, they should look completely different one from the other. They should have different temperatures, they should have different properties, and so on. But yet, as I told you, when we observe this cosmic microwave background, we find exactly the same temperature, 2.7 K, in all of those patches, up to tiny fluctuations of order 10 to the minus 5. So it does not disprove the model. Okay, you could imagine that someone fine-tuned properties of the universe 400,000 times and took the same initial condition in all of those patches. But this is not very satisfactory as an answer. We would like to understand why we have the same initial condition in patches which, in principle, share absolutely no causality. So this is called the horizon problem. And you see immediately from the way that I have introduced it that a solution to this problem would be found if you imagine that there is a phase early on where this condition is not satisfied. Okay? So if there is a phase where A double dot is positive, and therefore P is greater than 1, and that would give rise to a much larger value of d naught. In fact, even d naught could be infinite. And this idea of having an early phase with A double dot positive is called inflation. Okay, so nowadays inflation is almost considered as being part of the standard model itself, because it's one of the best explanations we have for this horizon problem and for many other things. But historically it was of course added at a much later stage. So the idea is that, okay, we can have this phase of accelerated expansion, A double dot positive. It's of course just a hypothesis for the moment. We call it inflation because the universe expands in an accelerated way. One thing you can show is that if you want to realize this phase of inflation with a perfect fluid, okay, so you take the universe and you fill it with a fluid with energy density rho and pressure P, and then you use your Einstein equations to see at which rate the universe expands. The Einstein equations, they give you this equation, A double dot over A is minus 1 over 6 times the Planck mass squared of rho plus 3p. So you see that if you want A double dot to be positive, you need rho plus 3p to be negative, which of course you cannot achieve with usual fluids, because energy density is positive and pressure is positive. So this is why I was saying before that for regular fluids, A double dot is negative in cosmology. However, if this phase of inflation happens very early on, it happens at energy scales which are super high. And at those energy scales, we don't expect to be able to model matter with just low energy fluids. In fact, we should use our best theory of high energy physics, which is quantum field theory. And it turns out that if you consider the simplest field that you can think of, which is just a scalar field, you can show that cosmology with a scalar field is analogous to the one of a perfect fluid if you replace the energy density and the pressure with those expressions. So the first equation is quite intuitive. It tells you that the energy density is a sum of a kinetic energy and the potential energy. V of phi is the potential energy which is stored in the field phi. But the pressure is the difference between those two terms. And because there is this crucial minus sign here, it means that whenever the potential energy is greater than the kinetic energy, in fact greater than 2 times the kinetic energy, then this rho plus 3p becomes negative and A double dot becomes positive. Okay, so the conclusion from that is that if you can find a scalar field somewhere in your theory which possesses a potential energy that is such that potential energy is greater than 2 times its kinetic energy, then you have found a good model for inflation. So said like this, it sounds easy. In practice, it's not so easy. The reason is that if you want the potential energy to dominate over the kinetic energy, you need the kinetic energy to be small. So you need the field to be rolling at a very slow rate in the potential function, which means you need the potential function to be almost flat. And in high energy physics, finding flat or almost flat potentials is challenging. Usually some corrections, loop corrections make the potential function steeper. But there are some good candidates for this scalar field, which could realize a phase of early inflation. So at this moment, there is no reason to be too much convinced by inflation because I've just introduced it to solve a problem that was already there. So of course, it solves the problem that it was meant to solve, but this is it. What really made inflation popular is the following thing. It is that inflation makes a prediction not only for the global structure of the universe, but also for the fluctuations that we should find in it. And the reason is the following. So if you take, again, this very easy metric, this easy geometry, there is a single parameter, dimensionful parameter, which you can construct, which is just a dot over a. So this has dimension of 1 over time, so 1 over length, if you set c to 1. So 1 over h is, say, the typical time scale, the typical length scale of which characterizes the curvature of your space-time. And now let's see what happens if you put some quantum field or some field on top of this expanding background. So what you find is that, okay, space here is homogeneous, so you can Fourier expand your field. And then you can look at the dynamics of each Fourier mode, because all those Fourier modes decouple. And what you find is that the dynamics will depend very much on whether the wavelength associated to your Fourier mode is smaller than this radius of curvature or whether it's bigger than this radius. If it's smaller, it means that you're probing physics at scales which are much, much smaller than the curvature radius, so you don't really see the curvature. It's a bit like, if you want to measure the distance of things inside this room, you don't need to take into account the fact that we actually live on the Earth, which is a curved sphere. The distances here are much, much smaller than the radius of the Earth, and so we don't care about the curvature of the Earth. But if you want to perform measurements of distances between Padova and, Tokyo, then of course you have to, depending on whether the light goes in a straight line or whether it goes through the surface of the Earth, you will find very different results. So you do need to worry about the fact that you live on a curved surface. And the same happens here, so you only feel the curvature of space-time when the wavelength becomes larger than the Hubble radius. So if you live in this regime on the left-hand side, you don't see space-time curvature, which means that it's the same as physics in flat space-time, okay, in Minkowski space-time, so we can define a vacuum state and everything goes as usual. But in this regime on the right-hand side, we feel the curvature. And whenever in quantum field theory, you can show that whenever you have a quantum field on top of a curved space-time, you typically have particle production. Okay, so there are well-known examples of that. One example is so-called Hawking radiation, which is the fact that if you get close to a black hole, the curvature of space-time becomes so strong that you can spontaneously create pairs of particles and antiparticles. And there is a flux of particles which radiate away from the black hole if you sit very far away from the black hole, which you receive as a so-called Hawking radiation. There is the Schwinger effect, which is another example. But in cosmology, we have, again, another example of that, which is that we create particles at all scales which are larger than this Hubble radius. Now, what inflation does is that it provides a transition between those two regimes. Okay, so during inflation, all the scales, they undergo a transition between this regime on the left-hand side where nothing exciting happens to this regime on the right-hand side where you have an explosive production of particles. The reason is that during inflation, you can show that if the potential function of the inflation is almost flat, you can show that the Hubble radius is almost a constant. So this Hubble radius is almost a constant, and the wavelength of your Fourier modes, they grow just because space is expanding. Okay, so as a result, initially, all those scales, they lie inside the Hubble radius, where they start in the vacuum state of the theory without any particle. As soon as they cross the Hubble radius, you start to pump particles out of the vacuum and to create perturbations, cosmological perturbations. Now, the nice thing is that if you compute the statistics of those fluctuations that you create out of the vacuum, and if you compare with what you observe in the cosmic microwave background, then you find a perfect match. Okay, so I think I have a plot, which shows that more explicitly. So how do we do it in practice? So in practice, we have to quantize not only the field that drives inflation, which is a scalar field, the phi, or fluctuations of this field, but also the metric, also the fluctuations of the metric itself. The reason is that, so it's a technical reason, but general relativity is a theory which is invariant under changes of coordinates. Okay, so you can change the coordinates of your system for space-time, and it doesn't change the theory. And you can show that whenever you perform this change of coordinates, typically you mix fluctuations of the matter fields and fluctuations of the metric, which means that the only quantity in the theory which do not depend on the choice of coordinates, which we call gauge invariant quantities for obvious reasons, the only quantities which do not depend on those choices, they are linear combinations of fluctuations of the scalar field and the metric. Okay, so you can show that there is one combination which is relevant, which is called the Mukhanov-Sasaki combination. The name does not matter. I call it V here. So it's a linear combination of delta phi and of all the delta g mu nu. It does not depend on the choice of coordinates, and this is the thing which we describe as a quantum field starting from the vacuum state. Okay, this is called the Bunch-Davies vacuum, but again, the name does not really matter. And this field V, you can show, is directly proportional to the temperature fluctuation of the cosmic microwave background. So when we observe the temperature of photons in different directions, it is in fact this field V that we are observing. So what you see in this plot here is a comparison between the theory, which I've just described, and the measurements. So the red curve is the theory, the measurements are the blue dots. What it is in practice, it's a bit like a power spectrum. It's just that the CMB, we don't observe it in space, in three-dimensional space. We point the telescope in a direction where we receive some photons. So in fact, we observe it on a sphere. And on a sphere, you cannot do Fourier expansion. You do something analogous, which is called spherical harmonic expansion. But it's very analogous. The number which is called L here is the analogous of the Fourier mode, if you wish. So very small scales, they are on the right-hand side of the plot. Very large scales, they lie on the left-hand side. And here you have 2,500 measurement points, while the red curve is being fitted by only 6 parameters. Those parameters are cosmological parameters, like, for instance, the abundance of dark matter today, those kind of things. So we can fit 2,500 points with only 6 parameters. In fact, it's even better than that, because those photons, they don't only have a temperature, they also have a polarization. And we can measure the polarization of those photons. So this is if you wish, the cross power spectrum between the temperature and the polarization. They are independent, if you wish, independent measurements. But they are still extremely well fitted by these same 6 parameters. There are 2,000 data points, and this is the cross correlation between the polarization itself. Again, 2,000 data points, which are again extremely well fitted by the same 6 parameters as the left-hand plot. So this exquisite agreement between experiment and theory is is not evidence because we never prove anything, but is a good indication that what I've told you before is not completely crazy, and at least it provides a way to understand those measurements. So most people are extremely happy with that, and I mean, including me, but of course it raises some important questions. So the conclusion we draw here is that structure formation in the universe, so the birth of structures, galaxies, stars, planets, even you, anything which deviates from homogeneity, just proceeds from the amplification of quantum fluctuations. So the universe starts empty, there are some quantum fluctuations, they are amplified by gravitational instability, and this gives rise to all of these structures. But in fact, if you take it seriously, it's not so trivial, right? So first of all, you have to assume that quantum mechanics works at all of those scales that we have been dealing with. So the largest possible distances, those very high energies in the early universe. Quantum mechanics is a beautiful theory, but at the end of the day, we have been testing it only in the lab in some range of scales, of energies, of distances, and so on. So maybe one could think that maybe it doesn't work at those scales. And then there are questions which are maybe a bit more specific to using quantum mechanics in this context. For instance, I've been quantizing something which is a combination of the matter field and the metric, but we don't know exactly whether we could quantize the metric. We know that if we try to quantize the full metric, we run into some divergences that we don't know how to deal with. It's the problem of so-called quantum gravity. We don't have a well-understood theory of quantum gravity at this point. Of course, here I don't do quantum gravity because I only quantize the fluctuations of the metric. I assume that the metric is given by a classical part, which is not quantized, which just obeys classical physics, and I just quantize the fluctuations. This is why I can do the calculation I do, but still one could argue that maybe there is something which prevents you from quantizing anything related to the metric. There is also a question related to the so-called quantum measurement problem. So you know that in quantum mechanics, systems can be placed in a quantum superposition, and the Copenhagen interpretation is that if an observer comes around and performs a measurement, the wave function collapses to one of the eigenstates of the operator you measure, and in particular it collapses to the eigenstate that gives you the eigenvalue that you have measured. So there is a division. The world is divided between a system and an observer, and this is perfectly consistent with what we observe in the lab. But in cosmology, of course, you cannot make this splitting, right? There is not a system and an observer. The system now is the entire universe, so there is no observer outside of the system. In fact, if you are the observer, you are yourself part of the system, right? Because you live in this universe, you cannot get out of it. So whether this interpretation really works in the cosmological context is not very clear, so it's maybe one other motivation to test the validity of quantum mechanics in this picture. And another way to look at it is that, well, there are some alternatives to this Copenhagen interpretation I was mentioning before. There are some alternative formulations of quantum mechanics. For instance, there is one which is called dynamical collapse models, in which you add some nonlinear corrections to the Schrödinger equation. This theory gives you different predictions as usual quantum mechanics. And people have been trying to test it in some experiments in the lab. But in fact, if you apply it to describe the early universe, you can also constrain it in a completely different range of scales and energies. So another way to look at it is to say that the universe gives you, another playground or another place to test for quantum mechanics and alternatives to standard quantum mechanics. Okay, I won't be talking about those collapse models, but just to mention that this can be discussed as well. So because of that, there is, I think, good motivation to try to test whether we can prove that cosmic structures, they have a quantum mechanical origins. I should also say that here I will mostly mention inflation because that's the leading theory that people study. However, it's not the unique one. There are some alternatives to inflation. For instance, contracting cosmology, so universes which contract and then bounce and then expand again. But in fact, all of those alternatives, apart from one, but all of those alternatives, they rely on a similar mechanism to produce cosmological structures. So they also rely on gravitational instability out of quantum fluctuations. So what I will discuss here would also apply to those alternatives, but for explicitness, I will mention inflation to have something concrete. But those alternatives, they would also we could also discuss them. Okay, so the idea is that this is a strong statement, the fact that cosmic structures come from quantum fluctuations. So somehow if it's an extraordinary statement, that would require some extraordinary evidence. What people usually think is that, well, the consequences that you can infer from this idea are consistent with observations, and somehow it's a good validation of the of the theory, which is correct, but it's only an indirect confirmation. Okay, so what I would like to be after here is not some indirect way, some consistency check. I would like to have a way to really prove or disprove that cosmological structures, they have a quantum mechanical origin. So it's a long talk. Of course, it's not something which I'm the only one being interested in. A lot of people have worked on it since a long time ago. The earlier works on it date back from the late 90s. And there are lots of ways we can approach this. I'm sure I've forgotten many people on this list. It would easily fill the entire slide, or maybe 2 slides. But I will just focus on a few ideas just to give you a glimpse of the kind of thing that we can do with that. Yeah, maybe I've been too slow, no? I will maybe focus on a few ideas. So one key statement is that why are the quantum and classical worlds different? Well, they're different because they allow for different types of correlations. And the very famous example is the so-called Bell inequalities, which were the experimental proof of which were given the Nobel Prize last year. And in those Bell inequalities, what you do is that you produce some entangled particles, and you have 2 observers, Alice and Bob, A and B, which measures the spin of those particles in different directions, and then they compare their results. And they find that the results they find are correlated. Okay, so when Alice finds spin up, Bob has some probability to find spin up, which is not 1/2, which is... so those results are correlated, but they are correlated in a way that you cannot explain by classical correlation, so you cannot find the classical distribution of probabilities that would reproduce this result. You have to in fact, to rely on the quantum formalism. So the question I would like to answer is, can we have something analogous in cosmology? Can we construct a Bell inequality for cosmology? So in practice, I have this beautiful cosmic microwave background measurement. I can measure things about those photons in different locations of the sky. I can construct some correlation functions, and the question is, could I find some correlation function? Could I find some observable that would give me an answer of the type this cannot be explained with classical correlations, and this has to be quantum or not. So in fact, okay, because I have, let me just skip a few things, sorry about that, to maybe focus on, yes, so maybe, okay, let me maybe explain this, because it's kind of interesting. I find it interesting and not so often discussed. So when you want to perform Bell inequalities, you need to have you need to have a few things. Okay, so let's review exactly what we need. The first thing is you need to have a bipartite system, so you need to split the system between 2 parts, A and B. And one thing you can do in cosmology is that because you have a field, a quantum field, you can show that particles are being created with opposite wave momenta. This is because the theory is isotropic, so you need to preserve isotropy. So if you have a particle with momentum k, you need to create a particle with momentum minus k. And those particles are created in an entangled way. So a good splitting of the system is to look at the mode k and the mode minus k. And this will provide you an bipartite system in an entangled state. So this entangled state is called a 2-mode squeeze state, but it does not really matter. Then we need 2 things. One is we need spin-like operators. So in Bell experiment, Bell imagined the Bell inequalities by measuring some spin operator. But here it's a scalar field. Okay? So it's not something which takes value plus h bar or minus h bar over 2. It takes a value which is continuous. It's a temperature field that you are measuring. So one first question is how do you build a spin operator or a set of spin operators out of a continuous variable? And then there is another question which is related to the nature of the Wigner function. So this I will explain because I find it interesting. So in fact, Bell himself wrote in a paper in 1986 that you can never violate Bell inequalities if the state has a positive Wigner function. And so I will explain why he said that. And then I will explain why, in fact, it's incorrect. And if it was correct, then this would be the end of the story because the Wigner function for us is positive. So the reason is the following. So first of all, let's explain what the Wigner function is. So when you have a wave function, psi of some position variable, which here I call V, because V is the Mukhanov-Sasaki variable, this thing which describes cosmological fluctuations. So V has a conjugated momentum P. So phase space is described by V and P for every mode K. So you have a Vk and a Pk. And you can construct this Wigner function, which is a little bit like a Fourier transform of the wave function. It's called the Wigner-Weil transform. But the details do not really matter. What matters is that it's just another way to describe the state. So you know when you have a wave function, you can describe a state, you can describe it with a wave function or with a density matrix, or in fact also with a Wigner function. Those are equivalent descriptions. And as it turns out, if you do this for the state of cosmological perturbations during inflation, you find that this W of V and P function is a Gaussian function. Okay, so it's a very easy state. We call it a Gaussian state, which means the Wigner function is indeed Gaussian. And we call it a squeezed state just because as time proceeds, this Gaussian becomes more and more squeezed in one direction and more spread in the other direction. Now, this Wigner function has some nice properties. For instance, you can show that the equation of motion for the Wigner function, if you do a d over dt of this W, if the Hamiltonian is quadratic, which I assume here because I work at leading order in the amplitude of those perturbations, so I only keep quadratic terms in the Hamiltonian, then you can show that the Wigner function obeys this equation, which is the time derivative equals the Poisson bracket with W. What it means, in fact, so what does it mean physically? It means that, you see, this is the Wigner function on the left at some initial time, so it's just some Gaussian. And on the right plot here, I've just drawn points randomly, but using this W as a distribution function. Because it's a positive function, I can interpret this as a distribution function, probability distribution function. It's normalized, it's properly normalized. And so I can draw points according to that distribution. And then I can let time evolve. And in fact, what happens is that, so what this equation is telling you is that if you use the classical equations of motion for each of those dots, okay, so I just use Hamilton equations, I evolve those dots in phase space using classical equations. So the cloud of points evolves, it spins, and then it gets squeezed in one direction and spread in the other direction. And at some later state, I reconstruct the distribution function that this is modeling. Then I obtain indeed the Wigner function. So the Wigner function is evolving exactly as a classical distribution function. So it looks very classical in this sense. Now the second thing is that you can also show that if you want to compute the expectation value of any quantum operator A, you can make use of this formula, which is that expectation value of A in your state is the integral of this Wigner function over phase space times another function of phase space, which I call A tilde, which is constructed out of A in a way that is similar to the Wigner-Weil transform. Okay, so out of any quantum operator A, you can construct a phase space function, A tilde of position and momentum. And you can show that the expectation value of A is just given by this integral. And again, if W is positive, you can interpret it as a distribution function. So in fact, any observable can be thought of as just coming from random classical processes you integrate over a distribution function. So for this reason, in 1986, as I was saying, John Bell said that Bell inequality violation requires non-positive Wigner function. And because the Wigner function for us is positive, we cannot violate Bell inequalities, and this is the end of the story. So fortunately, in 2006, Revzen published a paper which is which is very, very poorly cited, so I like to advertise this, which in fact showed that this is not true. This is of course correct, but this is correct only if the operators are called proper. And proper operators, it's a bit technical, they are operators for which this quantity A tilde, it only takes value inside the spectrum of the operator, which means inside the set of eigenvalues of the operator. But it's not difficult to construct quantum operators for which the Weil transform takes values outside the set of eigenvalues. And in this case, this theorem here does not hold. So, okay, I think I would just show you a plot, and then I will conclude. So you can construct those operators. I don't really have time to explain how, but essentially, so how do you construct a spin operator out of a quantum variable? One very easy way is to take the continuous set of eigenvalues, and then you divide it between some intervals of size L. L is a parameter that you can choose to be whatever you want. And then you assign +1 or -1 to those intervals alternatively. So if you measure the field here, you return +1. If you measure the field here, you return -1. So this operator is written formally here. It's called SZ. And you can show that you can find some similar expressions for a Sx and Sy operator, and that they satisfy the spin algebra. And that's a way to construct spin operators. And you can show also that Sz is a proper operator, but those other guys, Sx and Sy, they are improper operators. So you have some hope to violate Bell inequalities. And indeed, when you compute, so you can just focus on the right-hand plot here. So this is a plot of the expectation value of the Bell operator. It's called Bmax because you have this L parameter, which is a free parameter. So here I've taken it to be optimal. I've taken it to be the one that leads me to the maximal Bell inequality violation. R and phi are called squeezing parameters. They are just parameters which parameterize this two-mode squeeze state. So essentially, phi is you had this tilted ellipse for the Wigner function. Phi is the angle of the tilt, and r is how much you have squeezed the ellipse, kind of. And what you can show is that in this space, you have a set of points, which are the dark blue points, where you do not violate Bell inequalities. And then you have the set of points, which is yellow, red, and so on, for which you do violate Bell inequalities. Now, the funny thing, which is to me a coincidence, but maybe there is a deep reason. Of course, the question is where am I in this plot? And you can show that as inflation proceeds, so during inflation, R increases, so you get to the right. But so of course, if this is not good, because if you start here and R increases, you end up in the dark blue region. But also phi decreases. Okay, so the problem is at which rate does this happen? Is phi decreasing faster than R, or is R decreasing faster than phi? And this white dashed line here corresponds to a reference case for cosmology, which is called de Sitter expansion. So it's the case where inflation proceeds with a scale factor function, which is an exponential function of time. So a of t goes like exponential of t, exponential ht. And it so happens that this reference case, de Sitter, is exactly at the boundary between the non-violating and the violating region. So now we know from observation that we don't live in a de Sitter universe. Now we know that there are some deviations from de Sitter, which are confirmed by measurements of the CMB. And in fact, depending on the model of inflation, on the precise details of the way that inflation took place, you can either end up at the top above this line or below this line. Let's say in models where you end up below this line, you find yourself in a region where Bell inequalities are violated. So I think I should probably wrap up. Of course, so this is not the end of the story, because then the next question would be, okay, so can you make this experiment for real? Can you make this measurement? There are things which I have not talked about, in particular the fact that here I've considered my cosmological field as being isolated, so it's in a pure state, but in practice it's supposed to interact with other things. And when you have interactions with degrees of freedom that you do not observe, you typically have what is called quantum decoherence, which leads to the state being non-pure. And when the state is not pure, in principle, you erase some of the quantum features, so that could play a role. This is something that we have been working on, and people here are also working on it. So there are lots of different caveats and challenges that we still have to face. And it proves that it is a very difficult task. But if possible, of course, the reward will be great, because it's a very important aspect of cosmology that cosmological structures come from quantum fluctuations. Okay, maybe it's best if I stop here, I guess. Yeah.
Thank you. Thank you very much, Vincent, for this nice overview of some of the issues behind this quantum nature of cosmological fluctuations. So, questions?
Hello. The graph on the left,
Yes.
why is its pattern so irregular compared to the others?
I don't know. It's a
What does it say?
So I don't really know. So what it is the expectation value of the Bell operator for fixed parameters. So here I look at a fixed quantum state, which is given by some fixed value of the squeezing angle and fixed value of the squeezing amplitude. And then I compute this expectation value of the Bell operator for different parameters L. And L is the thing which characterizes, if you wish, the coarse graining with which I've splitted my, so the way that I split the real, the continuous variable into +1, -1, +1, -1. And you're right that the pattern is super weird. In a sense, you have those features which arise in some places. And yeah, I don't know. Yeah.
Thank you.
So are there also artificial cases in which we could create something that might violate the Bell's inequalities so that we could measure?
So cases where you end up below the white line, you mean? Or
yeah, in the red part, I guess.
Yeah. So there are models of, in fact, if you so like I was saying, if you measure the CMB, you know that we don't live on inflation did not proceed along the white line. This is now excluded at, like, I don't know, 7 sigma or something like that. But we can say something more. We can constrain a bit more the rate at which inflation took place. And the measurements we have, they give a preference for being below the white line. If you try, so there are measurements on quantities which describe the correlation functions of the fluctuation that we measure. If you translate those into those parameters R and phi, it will tell you that you have some strong preference for living below. So it's not, yeah.
Yes. Just to understand, I mean, could you say in simple words, suppose one wants really to make an experiment to
yes.
measure this kind of correlation. So what should be measured concretely? I mean, which kind of experiment can one figure out?
Yes. So it's a very good question. So there are lots of things that are on the way between this and a concrete experiment. So let me just mention a few. One is that here it's a correlation between k and minus k. But this has no meaning, but in practice we do not perform measurements in Fourier space, we perform measurements in real space. And also Bell inequalities, they are violated by local theories with hidden variables. But locality is of course a property which holds in real space, not in Fourier space, it doesn't mean anything. So first you have to convert this into a statement in real space, and this has been done, but there you show that it's more difficult to violate those Bell inequalities. The second statement is that we observe, at the end of the day, we observe one single thing, which is the temperature fluctuation. And maybe the polarization of the photons. But if you only have one observable, you don't have non-commuting operators because you have only one. So this is the problem of the so-called decaying mode in cosmology, that there is position and momentum. The position is something which grows, the momentum decays, and it decays to very, very small values which are difficult to measure. So it means that those operators that I have introduced, the spin operators, one of them can be directly measured from the temperature, but the other one somehow they would require to access this decaying mode, which has a very small amplitude. So here as well, there are some possible ways out. For instance, there is something which is called temporal Bell inequalities, in which you don't, instead of measuring two parts of the system at the same time, you measure them at different times. Or you can even measure the same system at different times. This is called the Leggett-Gark inequality. And in this case, you can do this by measuring only one operator. You don't have to rely on non-commuting operators. But if I wanted to do this in practice, it would mean that I cannot only use the cosmic microwave background because the cosmic microwave background is roughly a single time event. Not exactly because it does not happen at the same time, exactly at this, but roughly speaking, it's just a snapshot of the universe. So if I wanted to do this, I would have to construct correlations between the cosmic microwave background and some later times measurements. So we have some later time measurements because we also observe distributions of galaxies, for instance, which are other snapshots of the density field, but at some later times. But I would have to construct some, correlators between those different maps. And this is also a very, very big challenge. So it's still a very, very long way. I'm very far from proposing an experiment that, give me $1 billion and I built it.
Are you afraid that coherence could be lost in the process? Because
so this is so of course it's another big concern that decoherence takes place and washes all of those things away. So in fact, there is something funny which happens, which is that so those states, they become very squeezed, and squeezed states are known to be kind of fragile in the sense that if you couple them to some environment, they easily decohere. But on the other hand, when you ask the question, so you can redo this analysis for a squeezed state which has decohered. And what you find is that, in fact, whether or not you violate the Bell inequality does not only depend on whether or not the state has decohered, so there is a trade-off between the amount of squeezing and the amount of decoherence, so to say. And in fact, because squeezing increases as a function of time very quickly, you find that the decoherence rate needs to be very, very large. So not only you need perturbations to decohere, but you need them to decohere at a very, very, very large rate. And so at the end of the day, it could be that we are protected from it.
If I understood well, you prefer to be in the lower,
Yes.
Below the white line, because above the Bell equality is violated.
Yes.
But since your seminar was on structure formation, could you say that above the white line there are no structure formations, or at least not the structure formations we see, and while below the white line we can see the structures as we see them today?
No, so structural formation would take place anywhere here, but my statement is that if I measured, if I measured this Bell operator, if I did this, if I carried out this Bell experiment, then I wouldn't find any violation of the Bell inequality above the white line. I would find structures in the universe, but there would be nothing which at least from that experiment, there would be nothing that would tell me that they have to come from, that they violate classical probabilities.
So this kind of structure formation would have a purely classical explanation.
So this statement is hard to make. So at least, because if I violate Bell inequalities with that construction, it's a sufficient condition to say they have a quantum mechanical origin. But if I don't find violation, I cannot say that they have a classical origin. I can just say that, okay, because this construction is not unique, so Bell inequalities are not unique. I can imagine other set of spin operators, and in fact, there are some other spin operators which have been proposed. And it does not tell me that maybe you can find a more clever way and you will unveil the quantum origins, but at least this will not work.
So at some point you mentioned about the alternatives to inflation, right? So I'm just wondering whether we can expect some differentiable signature in this kind of operators also for like a difference in the initial state.
Yes, so there are quite a few different alternatives, but let's say most of them they rely. So the difference between inflation and those alternatives is that the evolution of the background, so the rate at which the universe contracts or expands, is different. And so what you can show is that inflation is not the unique way of solving the horizon problem. If you have a contracting cosmology which then expands, you also solve the horizon problem. Of course, those models, they have one big question mark, which is what happens between the contracting phase and the expanding phase. So here you need to have a so-called bounce. So what people typically assume is that a bounce is naturally expected from a quantum gravitational point of view, because you know that in quantum mechanics you cannot take a system and make it as small as you want. At some point there is Heisenberg uncertainty. There should be So if the universe contracts, something should make it bounce. But the details of that process, we don't really understand them. So most of the time, people just assume that there is a bounce. But if there is indeed a contracting phase and then an expanding phase connected by a bounce, then you can solve the horizon problem. And then if you want, so then you also amplify quantum fluctuations out of the vacuum and so on. And you also place them in a two-mode squeeze state. So this is going to be the same state with parameters r and phi, which depend on the model that you have. But those parameters, they are kind of, if you want, they are measured when you observe the cosmic microwave background, so they're constrained in the same way. So, at least at leading order, there are no difference, right?
Thanks.
Okay, I don't know whether there are other questions or comments.
Previously in your presentation, you mentioned if the uncertainness that arises from quantum mechanics extends to cosmology. And I was wondering if you had just any personal convictions about that.
So, okay, one personal opinion I have is that I'm a bit bothered by the quantum measurement problem, namely the fact that the theory predicts that, all the fields in cosmology, they are initially placed in a quantum superposition. So, I mean, if you really buy, if nothing happens, you should predict that galaxies, they form themselves in a quantum superposition, okay? So the Milky Way should be in a quantum superposition of being here and somewhere else. And of course, this is a silly thing to say, but we don't know what such a universe would look like. It does not make sense. So there has to be a transition between this quantum superposition and some definite, some well-defined realization of the field. And the way this occurs in cosmology makes me feel a bit uncomfortable because there is no, So this makes me feel a bit uncomfortable. And this is also one of the motivations I have is that, if I push really this reasoning to the end, then I should be able to see some quantum signature. Or maybe something happened that, that removed those quantum superposition, which is not a mechanism which is included in quantum mechanics already, but which comes from something else. But but that's the thing. Quantum mechanics is super successful, is tested to super high accuracy in all the situations we know. There is no reason to believe that it fails anywhere because there is no indication of its failure. But just for conceptual reasons, I think, there could be something happening. Yeah.
Okay, other questions? So if not, maybe I just have one, if I can, I take my chance. No, I mean, here you are also always mentioning, of course, CMB fluctuations and temperature and polarization, because, of course, it is one of the cleanest cosmological probe. This means, of course, to focus on some scales, okay, which are essentially the largest one. Now, I just was wondering, what about probing other scale and probably smaller scales where maybe you could have actually the chance to see some relic quantum signatures?
Yes.
If you could comment eventually about that.
So there are lots of good reasons to consider smaller scales. And at least there are two. I mean, one is that if we go back to the concern of decoherence, so as you know, we expect decoherence to be less efficient at smaller scales. So it could be that large scales have decohered, but maybe some quantum signature remained at small scales. And the other thing is this problem of the decaying mode, so the fact that we have a huge hierarchy between, say, position and momentum, is that this ratio between the growing and the decaying mode becomes smaller at smaller scales. So it means that if you consider smaller scales, the decaying mode is less erased. And so maybe this would be a way to solve it. There are also models of inflation which deviate from the usual regime towards the end of inflation. And those models are discussed a lot at the moment because they give rise to some amplifications in the fluctuations, in the density fluctuations. And those increased density fluctuations, they could give rise to primordial black holes, which are very popular at the moment to explain a few things that we observe in cosmology. But in fact, in those models, because you deviate from the standard regime, from the slow regime, the growing mode and the decaying mode, they behave in different ways. And in fact, at those scales, they are scales at which they have, in fact, the same amplitude. So that would be an excellent candidate for quantum signatures because they would be, highly excited because large density fluctuations, but still the two modes would have the same amplitude. And because they are small scale, it's very likely that they undergo little decoherence. That would be ideal. But of course, those scales, so we don't observe them in the cosmic microwave background. It's not clear exactly, down to which scales we need to go. But yeah, that would be.
Could have other probes.
Yes, we could. Yeah.
For those smaller scales.
Yes, absolutely.
So. Okay. So I think we can stop here. So let me thank again everybody to come here in person, and let me thank once more Vincent Vennin for the colloquium. Thanks a lot to everybody.